Hello, everyone. My name is Mina. I am a graduate student in the Electrical Engineering Department working with Professor Grace Gao at Stanford University. And today I'll be presenting our work on designing low correlation GPS spreading code sequences using a policy gradient-based reinforcement learning algorithm. Earlier this year, the United States Air Force announced that the first GPS-3 satellite was marked healthy and available for use. And this modernized constellation is distinguished by its reprogrammable payload, which allows it to evolve with new technologies. And additionally, with the upcoming launch of the reinvigorated navigation technology satellite platform, as well as the corresponding request for information announcements, the Air Force Research Lab has expressed interest in exploring modifications to all layers of the GPS signal in order to enhance PNT resiliency and performance. We are entering a new era of satellite navigation, and correspondingly, it's time to revisit the design methods of the GPS spreading code signals. Currently, all GPS signals use algorithmically generable spreading codes. The L1CA legacy signal, for example, uses gold codes, which can be generated with two 10-bit linear shift feedback registers. And the modernized L1C signal to be broadcast on the GPS-3 satellites uses whale codes, and these are generable using the Legendre sequence, and they also incorporate a 7-bit pad to satisfy the desired L1C spreading code length. Having algorithmically generable sequences was an important design consideration during the initial development phase of GPS in the 1970s, and this was due to memory storage constraints as well as computation limitations, which restricted the ability to search for better sequences. However, today, memory is an inexpensive resource, and receivers can readily store complete families of spreading code sequences. And spreading codes, which are not algorithmically generable, are also called memory codes. And by expanding the design space to the set of all possible binary sequences, we have a greater range of possible code families. Additionally, memory codes are not limited to a specific length of code sequence. Designing a non-conforming length of spreading code signal would require either truncation or extension of the algorithmically generable sequences, which would disturb the correlation properties of these codes. Although a larger design space provides a better opportunity to find a superior set of codes, it also greatly complicates the code design method. And several past works have designed memory codes using genetic algorithms for the Galileo satellite constellation. A genetic algorithm is a population-based optimization heuristic, which mimics the process of biological evolution by selecting and recombining strong candidates from the current population design points. And genetic algorithms were used for the Galileo E-band signals to design spreading codes which have the autocorrelation side lobe zero property, where the autocorrelation is zero at a relative delay of plus or minus 1 chip. And work has also been done to define several cost parameters for selecting high-quality GNSS spreading codes, such as evaluating the mean squared auto and cross-correlation components above the Welsh bound. And additionally, at last year's ION GNSS Plus conference, we proposed a multi-objective genetic algorithm platform for designing navigation spreading codes. And our algorithm improved on two objectives simultaneously. That was the mean absolute auto correlation and the mean absolute cross correlation of the code family. And reinforcement learning techniques have also been explored to generate error correcting codes. And these are binary sequences that encode messages to improve the detection of communication transmission errors. And reinforcement learning has been shown to be a promising framework for intelligent decision making. So in this work, we seek to explore using reinforcement learning techniques for the application of navigation spreading code design. In this work, we develop a policy gradient reinforcement learning algorithm which constructs high-quality families of spreading code sequences. And we use a Gaussian policy to represent a distribution over the action space, which designs the binary codes. We incorporate a baseline to reduce the variance of the policy gradient estimate, and this also improves the agent's rate of learning. And furthermore, to the best of our knowledge, this is the first work which explores using a machine learning approach for designing spreading code signals for navigation. And with our algorithm, we demonstrate the ability to achieve low auto and cross correlation side peaks within the family of spreading codes. And we also compare the correlation performance of our learned spreading codes with those of well-chosen families of equal length gold codes and whale codes. And we also compare with analogous genetic algorithm implementation, which is assigned the same code evaluation metric as our proposed algorithm. So first I'll describe our high-level reinforcement learning framework, and then I'll provide an overview of policy gradient reinforcement learning methods in general. Then I'll discuss our proposed Gaussian policy gradient algorithm, and that includes the policy function representation as well as the evaluation metrics used. And finally, I'll present the experimental validation before summarizing our work. So in the reinforcement learning context, the goal is to teach an agent to perform actions or to follow a policy pi which maximize its total received reward. And for our application, the reinforcement learning agent is a code generator, which takes in an initial set of spreading codes and then follows its policy to output a modified code sequence. And the resulting action is then evaluated and assigned a reward value by the code evaluator, which is then used to update the agent's policy parameters and improve its policy. And indeed, we can model the binary spreading code design process as a discrete Markov decision process, where the state space represents the space of spreading code families, and each state is a binary sequence. And the action space represents the set of bits to toggle in the current state. The transition function is a deterministic function which updates the code sequence state, and the reward function is an evaluation metric which is based on the auto and cross correlation properties of the spreading codes. So now I'll first provide a brief overview of the policy gradient reinforcement learning methods. So policy gradient methods are a subset of reinforcement learning algorithms which directly optimize over a family of parameterized policy functions. And a policy, which is represented here as pi, represents a probability density function over the action space conditioned on the current state of the agent. And policy gradient methods optimize the agent's policy function with respect to the expected total reward that's received, and that's represented as the function j. And the stochasticity of the policy function leads the agent to explore actions and to further improve its policy. And these methods, policy gradient methods, they're especially useful for reinforcement learning problems which have large action spaces, including even continuous or combinatorial action spaces, which applies to our application of interest with the design of navigation spreading codes. And a standard policy gradient algorithm is known as reinforce. And this samples trajectories by executing the agent's current policy, then estimates the gradient of the objective function by using the log likelihood of the policy function. And finally, using any first order optimizer like standard gradient descent or ATOM, we update the policy parameter theta. And this optimization process increases the probability of actions which lead to high rewards while decreasing the probability of those which result in low rewards. So now I'll discuss the details of our Gaussian policy gradient algorithm for designing spreading code sequences. We represent the policy function as a distribution over the set of bits to toggle from the initial state. And this is the initial code set and this policy function could be represented as a sequence of independent Bernoulli distributions, for example. Thus, for the agent to output a modified code set, it must sample from the toggle distribution, and that toggle distribution is provided from its currently learned policy function. And we represent the policy of the reinforcement learning agent using a neural network architecture. And this network takes in an input code set and outputs a toggle distribution. As a result, the parameters of the policy theta correspond to the parameters of the hidden layers of the network. And we model this toggle distribution using a Gaussian policy function, which I will describe in more detail in the next slide. And we choose the size of the network hidden layers to be twice the size of the code set, which is proportional to the code length and the family size. And for our application, we model the set of code design policies as an uncorrelated multivariate Gaussian family, where each component corresponds to an index in the binary code sequence and represents a univariate Gaussian distribution over the action of whether to toggle or not toggle that corresponding binary value. And our neural network model represents this Gaussian policy function by parameterizing the mean vector of the toggle distribution using a bounded output activation function. And the variance of each component is maintained as a constant value. Thus, for the agent to obtain a random bit toggling action from the policy function, it must sample from the multivariate Gaussian policy and then discretize each component according to a threshold. And this threshold corresponds to the midpoint of the bounded output range of the neural network model. And if the sampled component is above the threshold, then the agent toggles that corresponding bit value in the code sequence. Otherwise, the agent takes a no toggle action for that bit value. So to learn a useful set of spreading codes, the agent must learn to minimize both the autocorrelation and the cross-correlation characteristics of the generated code set. In this way, the evaluation metric provides the agent feedback to improve its policy function for code generation. And we use the mean square non-central periodic autocorrelation and the mean square non-central, or the mean square periodic cross-correlation as the two objectives to minimize. And in order to ensure that the agent reduces both objectives, we set the reward as the negative of the maximum of the two components. And as a result, for the agent to maximize its total received reward, it must reduce both objectives simultaneously without compromising one objective over the other. And finally, to reduce the variance of the policy gradient optimization step, we incorporate a constant baseline, which is subtracted from the return. And subtracting a constant value doesn't introduce any bias in the gradient estimate, but it can significantly reduce its variance. And in this way, by reducing the variance of the policy gradient estimate, we observe improved convergence and overall learning performance of the agent. And in this work, we use a simple baseline of the mean return in the current batch. So now I'll present our experimental setup and results. We validate the ability of our algorithm to output low correlation spreading code sequences, and we also compare its performance with those of well-chosen families of equal length gold codes and whale codes. And gold codes can only be generated for sequences of length 2 to the power k minus 1, where k is an integer that's not divisible by 4. And as a result, we compare the performance of our algorithm with gold codes of length 63, 127, and 511 bits. And similarly, since whale codes only exist for sequences that correspond to a prime number length, we compare our algorithm with whale codes of length 67, 127, 257, and 521 bits. And we generate sequences for family sizes of up to 31 codes, and we compare with the best performing code set across 10,000 sampled families of gold codes and whale codes. And the details of our policy gradient method are shown in the table. In particular, we use the hyperbolic tangent function as our bounded output activation function, and we use Atom as the optimizer of the policy gradient network, and we also use a batch size of 100 each iteration of the policy gradient method. And additionally, we compare the performance of our algorithm with that of an analogous genetic algorithm, which is programmed to optimize over the same code maximization evaluation objective. And the genetic algorithm uses fitness proportionate selection, which stochastically selects a candidate solution from the population with a probability that's proportional to its normalized objective. And the selected individuals are recombined using uniform crossover, and that allows for a greater recombination of the candidates, and we saw better performance of the algorithm with that crossover method. And we also incorporated elitism, and that ensures that the genetic algorithm will continuously improve during its optimization process. And finally, to make the genetic algorithm comparable with the policy gradient method, we set its population size to be the batch size of the policy gradient algorithm at 100 code sets. And we set the number of iterations for both algorithms to be the same. So here we can observe the effect of incorporating the constant mean baseline on the agent's learning performance. We plot the agent's performance on the normalized correlation objective for both methods, and we have two separate cases here. The first on the left is for a family of 5 length 63 codes, and the second on the right is for a family of 5 length 127 codes. And the learning curve shown in green represents the learning performance without baseline incorporation during training. And the curve shown in violet represents our proposed policy gradient method with the subtraction of the mean baseline. And from these example plots, we observe that the incorporation of the baseline leads to significant improvement in the overall learning performance of the reinforcement learning agent. And here we show the converged, normalized mean square, auto, and cross correlation performance of our policy gradient algorithm, while we compare it with the best gold and whale code families of equal length. Here we have the final performance of the length 63-bit sequences on the left, the length 67-bit sequences in the middle, and the length 127 sequences on the right. And the correlation performance results are shown as a function of the code family size, starting from a family size of 3 codes up to a family size of 31 codes. And the results of the gold codes are shown in gold, while the whale codes are shown in blue, and the results from our policy gradient algorithm are shown in violet. Also, the autocorrelation component of the objective is represented by the dashed lines, and the cross-correlation components are indicated by the solid lines. And here, we observe that for all 3 code lengths, the policy gradient method outperforms the best gold and whale code families in both objectives. And similarly, we plot the correlation performance of our policy gradient method for longer code sequences. Here we have length 27 sequences in the left, length 511 sequences in the middle, and length 521-bit sequences on the right. And because the tests were executed on my laptop, for sequences that were greater than 500 bits in length, we only conducted tests for family sizes of up to 15 codes. But by porting this algorithm to a system with more extensive computational resources with access to GPU devices and increased RAM, we would be able to perform optimization for larger code family sizes. But for each of the conducted tests, we observe here that for all 3 code lengths, the policy gradient method in violet outperforms the best gold and whale code families, which are shown in gold and blue, respectively. And finally, we compare our policy gradient method with that of the analogous genetic algorithm. Here we have the autocorrelation and cross-correlation performance results shown separately, and we show the results for length 127 and length 257 spreading code sequences. And the auto and cross-correlation performance of the genetic algorithm are shown in green, and here we observe that our policy gradient method outperforms the genetic algorithm in both correlation objectives for both sequence lengths. And similarly, performing the genetic algorithm for length 511 and length 527 sequences, we again observe that the policy gradient method surpasses both correlation objectives on these longer code sequences as well. And to summarize, in this work, we developed a reinforcement learning framework to devise a family of high-performing spreading code sequences, which can achieve low mean squared periodic autocorrelation and cross-correlation objectives. And we used a Gaussian policy gradient method to directly optimize the agent's bit toggling reinforcement learning policy. And we believe that this is the first work to develop a machine learning method to design navigation spreading code signals. And we also demonstrated the ability of our algorithm to construct higher performing codes than well-chosen conventional codes, including gold codes and whale codes, as well as the spreading sequences which were obtained from the genetic algorithm with the incorporated elitism. In particular, we observed that the policy gradient method outperforms these code sequences in both the autocorrelation and cross-correlation objectives. We would like to thank the Kirtland Air Force Research Lab, as well as the National Science Foundation for supporting this research work. And we would also like to thank the members of the NAV Lab research group for their thoughtful input on this work and paper. Thank you, and please feel free to leave any questions in the comment box.